Good afternoon to all of you. Myself Ankit Acharya, working as an assistant professor in mathematics in Hasmukh Goswami College of Engineering. Last time we discussed about vector space and we seen some example of vector space, subspace, linearly independent. So today our content is basis, dimension, linearly independent set and span of a set. So today's our content is basis, dimension, span of a set and linearly independent dependent. So let's see. This I want to recall that this is the definition of vector space, that closure under addition, commutative law, associative law, existence of identity, existence of negativeness, right? And these 5 conditions are for scalar multiplication that we seen last time. Okay, and we seen some examples of vector space, some important examples of vector space. This is another example that we seen last time. And next is a subspace. That subspace is a subset of a vector space, which is actually a vector space itself, a vector space under the same addition and scalar multiplication defined on V. And theorem, after that we seen linear combination of a vectors v1 v2 up to vr, and we seen some examples. We already seen some example of subspace. Okay, so starting from today's content, first of all, span of a set. Now what is a span of a set? Definition: if S is equal to v1 v2 up to vr is a set of vectors in a vector space V, then span of S is set of all linear combination of the vectors in S generated by v1 v2 up to vr. The span of S can be represented as theoretically alpha 1 v1 plus alpha 2 v2 up to alpha r vr, where each alpha I belongs to R for all I is equal to 1 2 up to R. So this is the definition of span of a set. Here we want to see some example. Now determine whether the following spans the vector space R3 or not. Now try to understand again the definition. What says the definition? Span of S is nothing but the linear combination, set of all linear combination of the vectors in S generated by v1 v2 up to vr. Okay, so that means one thing is sure, that for any set S is always a subset of span of S. S is always a subset of span of S. That is sure. Determine whether the following spans the vector space R3. Right? We want to check that the following vectors spans R3 or not. So for that, what we have to do? We are starting from any vector from R3 and try to find such constant such that for that ABC, AV1 plus BV2 plus CV3 is equal to V, right? If we can find such constant ABC, then we can say that this given 3 vectors spans R3, otherwise it not spans R3. So here we are starting from any XYZ belongs to R3 to prove there exists ABC, or to check, not to prove is not correct word, but to check there exists ABC such that AV1 plus BV2 plus CV3 is equal to V. So A into 2 minus 1 3 plus B into 4 1 2 plus C into 8 minus 1 8, that is equal to XYZ. If we can find such ABC, then we can say that the given 3 vectors spans R3, otherwise not. Okay, so let's see. again this is AB1 plus BV2 plus CV3 is equal to V. So that is A into 2 minus 1 3 plus B into 4 1 2 plus C into 8 minus 1 8, that is equal to XYZ. So from this equation we will get this three equations, that 2A plus 4B plus 8C is equal to X, minus A plus B minus C, that is equal to Y, and 3A plus 2B plus 8C is equal to Z. So from these three equations we convert into matrix. Okay, so here is the augmented matrix. We have minus 1 1 minus 1 Y, 2 4 8 X, 3 2 8 Z. So first we try to convert this matrix into row echelon form. So we multiply first row with 2 and add into second row. Again we multiply first row with 3 and add into third row. So the first entry of the second row and the first entry of the third row become 0. That means below the leading entry of first row become 0. So first row is minus 1 1 minus 1 Y, second row become 0 6 6 X plus 2Y, because we multiply first row with 2 and add into second row, and then third row becomes 0 5 5 and Z plus 3Y. Still, what is leading entry of second row? 6. So we have to make below that leading entry should be 0, right? So that 5 should be 0. We have to make that 5, instead of 5 we have to make 0. So what we have to do? We multiply second row with, or we multiply second row with 1 by 6. Okay, so we multiply second row with 5 by 6 and add into third row. Here two processes are once again, that we divide it by second row with 6 and then we multiply second row with minus 5 and add into third row. So that matrix become minus 1 1 minus 1 Y, 0 1 1 X plus 2Y 6 and 0 0 0 minus 5X plus 8Y plus 6Z by 6. So equation become minus A plus B minus C is equal to Y. Second equation become B plus C is equal to X plus 2Y by 6. In the third equation become minus 5x plus 8y plus 6z upon 6, that is equal to 0. But that is not possible for all x, y, z. So clearly V1, V2 and V3 does not span R3. Let's take one more example. V1 is equal to 2 2 2, V2 is equal to 0 0 3 and V3 is equal to 0 1 1. So for any V that is equal to XYZ belongs to R3, to prove there exist A, B and C such that AV1 plus BV2 plus CV3 is equal to V. So A into 2 2 2 plus B into 0 0 3 plus C into 0 1 1, that is equal to X Y Z. So from that equation we will get this equation 2A, that is equal to X, again 2A plus C is equal to Y, and 2A plus 3B plus C, that is equal to Z. Right, you can easily understand from the screen, that is A is equal to X by 2, C is equal to Y minus X, because C is equal to actually Y minus 2A, but 2A is equal to X, so C is equal to Y minus X, and B is equal to Z minus Y divided by 3. So V1, V2, we will get the ABC, we can find ABC in term of X, Y, Z easily. So that's why we can say that V1, V2 and V3 spans R3. Okay. Next topic is linearly independence and dependence of vectors. Now if S is equal to V1, V2 up to Vr is a non-empty set of vectors, if we take K1 V1, linear combination of that all vectors K1 V1 plus K2 V2 plus up to Kr Vr, that is equal to theta. Theta means 0 vector. Theta is a 0 vector of a given vector space. So if we take this equation K1 V1 plus K2 V2 plus up to Kr Vr is equal to theta, where theta is a 0 vector, and then if we will get all the scalars Ki is equal to 0, that means K1 is equal to 0, K2 is equal to 0 and Kr is equal to 0, then S is called linearly independent set. S is called linearly independent set. Otherwise they are linearly dependent set. Okay. Otherwise means what? What is the meaning of otherwise in this statement? Because otherwise means for any non-zero scalar, if this condition is satisfied for any non-zero scalar means either K1 is non-zero, either K2 is non-zero, or either Kr is non-zero. Any non-zero scalars, if this linear combination is satisfied, that means K1 V1 plus K2 V2 up to Kr Vr is equal to theta for any non-zero scalar. In that case we can say that V1 V2 up to Vr is a linearly dependent set. Okay. So just keep in mind this definition is very important. And one note here, that any set containing 0 vector theta become linearly dependent. That is quite clear. Using the definition you can easily prove that, because if any set containing non-zero 0 vector, that means what? We can multiply with non-zero numbers, because theta is a 0 vector, so k into theta is also a theta for any non-zero scalar. So when you take linear combination, you can take at least one non-zero scalar, such that linear combination of any vectors is equal to theta. So clearly any set containing 0 vector theta become linearly dependent. Okay. So that is you have to keep in mind, and this definition is very important. We will use in some examples. Now next is important result, you can say, or important statement that you can use to solve some examples very easily. What is the statement? You can see on the screen. If set S contain n vectors of Rn, exactly n vectors of Rn, then using determinant you can check the given set is linearly independent or not. If determinant is non-zero, then set S is linearly independent, otherwise it is dependent. Otherwise means if determinant is 0, the set S is linearly dependent. Okay. So just keep in mind that if determinant, and this condition, this statement you can use in example only in that case where number of vector is exactly the dimension of the vector space. That means in particular here Rn. Okay. So we dimension of Rn is n. So if your set contains exactly n vectors of Rn, then you can check the determinant, otherwise not. Okay. So check determinant. If determinant is non-zero, you can say that the given set is linearly independent. If determinant is 0, the given set is linearly dependent. And one another statement, that if set S contain n plus 1 vectors of Rn, then S is linearly dependent. Clearly or directly you can say that the given set is linearly dependent if that set contains more vectors than the dimension of vector space. So if set S contain n plus 1 vectors of Rn, then S is clearly linearly dependent. Okay. So we will use this true statement in some examples to solve some examples. So let's see. Check whether the given sets are linearly independent or not. First, here there are 3 examples you can see on the screen. Now first example, 2 1 1, 1 2 2 and 1 1 1. All the vectors are from R3. You can see all the vectors of R3, and S contains exactly 3 vectors. Okay. So this set contains 3 vectors of R3. So using the previous statement, you can check determinant, okay, to check linearly independent or not. Here to solve first example, we check determinant. 2 1 1 1 2 2 1 1 1. First row become 2 1 1 from first vector. Second row become second vector 1 2 2, and third row become third vector 1 1 1. Now determinant, to solve this determinant you will get 0. See, 2 into 2 minus 2 minus 1 into 1 minus 2, that is minus 1, and plus 1 into 1 minus 2, that is also minus 1. So 0 plus 1 minus 1. Okay, so that is equal to 0. So the value of determinant become 0. That means what? S is linearly dependent set. Using the previous theorem we can say. Check second example. Again in second example there are 3 vectors of R3. Okay, again there are 3 vectors of R3, 1 2 2 2 1 2 and 2 2 1. Check the determinant 1 2 2 2 1 2 2 2 1. When we check determinant, 1, that is equal to 1 into 1 minus 4 minus 2 into 2 minus 4 plus 2 into 4 minus 2, that is equal to